Okay. So first, I'd like to thank Celso in particular and the organizers for the opportunity to be here today. It's really a privilege and an honor, same as Juan and all the other speakers to be here. So over these 4 lecture series, we're going to talk about applications of quantum computing to quantum chemistry. It's going to be divided mostly into, the first part is going to be reviewing and introducing some concepts, and then the later part of the talks are going to be hands-on interactive exercises with the Jupyter notebooks that the organizers have shared with you. So, how many of you have heard about Xanadu before? A few, okay, not bad. So, if you don't know, Xanadu is a quantum computing company based in Toronto, Canada. We recently turned 8 years old, so it was founded in 2016, September 2016. We've grown very quickly since then. We're a little over 200 employees now. And everything that we do at Xanadu is guided by our mission statement, which is to build quantum computers that are useful and available to people everywhere. Our approach to doing that is a full stack approach. So Xanadu is actually primarily a hardware company. So we develop photonic architecture quantum computers. We've released a few generations. I won't really talk about the photonic architecture in these. Instead, I'm going to focus more on the pioneering quantum software side of things, in particular the PennyLane software library, as well as some directions on research and development in quantum algorithms, particularly as it pertains to quantum chemistry. So the plan for today is quickly introduce a little bit of the basics of quantum chemistry that you need to understand most of the lectures, just to bring everyone up to the same level. Introduce PennyLane a little bit, the format of how you do things in PennyLane. One thing I'd like to mention right off the bat, PennyLane is both a simulator and something you can use to connect to hardware, so that we don't spend the whole hour and a half just waiting in line to access a quantum computer. We're going to use it as a simulator. So it's just going to be running on your laptops, doing classical linear algebra in the background. But you'll get an idea of how certain circuits work and how certain algorithms work. And then as a first simple application, we're going to talk about the variational quantum eigensolver. And we're going to code it in PennyLane directly. So, I don't think I need to motivate this very much, but I'm going to bring back Richard Feynman, who was really, at least for physicists, the person who came up with the idea of quantum computing and why it's important in particular for simulations of quantum systems. And ultimately, the reason is, of course, molecules, superconductors, materials are ultimately quantum mechanical. Everything's quantum mechanical, really, but when you get down to a scale where it becomes relevant, it becomes really difficult to simulate with a classical computer. The reason for that is, of course, that the scale of a lot of these problems is far too big for computers, classical computers, to simulate efficiently. And I always like to emphasize these 2 words, certain problems and efficiently, because pushing back on some of the hype that you might hear, quantum computers won't be able to solve every computational problem, nor will they be able to solve problems that classical computers in principle wouldn't be able to. If you give a classical computer enough time, it'll be able to solve anything that a quantum computer can do. The difference is the time frame. Whereas a classical computer might take thousands or tens of thousands of years, a quantum computer might be able to do it in a few years. So that separation of time scale is really where this efficiently part comes from, and it's a big reason for the interest in developing quantum computers and quantum algorithms. Since the series is going to focus a lot on quantum chemistry, the ultimate goal or the dream of every quantum chemist is to be able to efficiently simulate a molecule of interest or material of interest, a collection of molecules of interest, really, to be able to determine certain properties about it. Typically, these are things like the energy, the dynamics of the system, the things like polarizability, different thermodynamic properties of these systems. And obviously, chemicals are all around us. We have a very large chemical industry all around the world that could benefit from a lot of these computationally assisted designs. So things like simulating chemical reactions, have interest in the energy sector, pharmaceuticals, manufacturing industries. A lot of it is still being explored, where exactly quantum computers will fit into all this, but there are a lot of applications that are being looked into. So you're probably all used to this picture of atoms. We typically think of atoms quantum mechanically as electron clouds, probability clouds, that follow certain interactions and certain rules defined by quantum mechanics. The probability cloud is, of course, an abstraction. What really seems to happen, at least the way that we interact with the quantum world, is that things are probabilistic. Every time you make a measurement, you have a series of possible outcomes, and you won't know which one will occur until you do the actual measurement. So in order to be able to simulate these quantum systems, you, of course, need computer simulations or software that can emulate this kind of probability that's inherent in quantum mechanical systems. So quantum chemistry, in some ways, can be broken down as trying to understand how molecules in a given configuration, in a given setting, interact with one another, and that will ultimately define the properties of the materials that they make up or the way that they interact with other chemicals. In principle, all of these collections of molecules can be described by a quantity that we call the Hamiltonian. If you don't come from a physics background, the Hamiltonian is essentially a way of encoding the energy of the system into a quantum mechanical operator, and this is going to be central to everything that we do in these series of lectures. The idea then is once you have access to this Hamiltonian, everything that you need to know about the system is described in this seemingly simple equation, which is, of course, the Schrodinger equation, in this case, the time-independent Schrodinger equation, where given some Hamiltonian acting on a wave function that describes the position of all of your electrons and molecules in your system, is described by this eigenvalue problem. The challenge, of course, is that when you get to very large molecules, this equation is impossible to solve even for classical computers. And this is, again, the great interest of being able to do this with quantum computers. You have quantum mechanical systems. You should have a quantum mechanical computer to simulate these. By the way, if there are any questions, feel free to interrupt me, raise a hand. It's easier to kind of answer questions as they come along. So for the first couple of these lectures, we're going to focus a lot on ground state energy estimation. The reason for that is because a lot of properties of molecules are ultimately determined by their ground state energy. So we're going to see a couple of different ways of doing that. We'll see things like estimating reaction rates in chemical reactions, I believe, tomorrow. We're going to talk about bandgap energies in a couple of lectures. And of course, just basic estimation of ground state energy, which is what we're going to do today with the VQE algorithm. The workhorse of a lot of quantum chemistry is a very simple tool known as the variational method, where you know that if you, by some miracle, were given the true wave function describing your ground state, and you have the Hamiltonian of your system, if you calculate the expectation value of that Hamiltonian given the true ground state wave function, you have the ground state energy that you're looking for. The idea of the variational method then is if you take literally any other wave function that depends on a series of parameters that I'm calling alpha here, you can estimate the expectation value of your Hamiltonian using this new wave function, and you'll get another estimate for the ground state energy that's going to depend on these parameters. And the crux of the variational method is that you're guaranteed that no matter what wave function you use, other than the true ground state wave function, the value of this energy E alpha is always going to be greater than the true ground state energy. So the idea then is you estimate this E alpha, you vary the parameters in a way that minimizes this value. And no matter how small you get, you're always guaranteed to be above the true ground state energy. So my question to you then, so this is the idea then, you guess any psi alpha. This is, of course, an educated guess. You insert a little bit of physics, a little bit of what you know about the system, and you want to minimize this quantity. So my question to you then is, what do you think the problem is with this method? Initialization of what? Yeah, what about it makes it difficult? Yeah, that's one. So one of the problems is as molecules get more and more complicated, it becomes more and more difficult to guess, to make a good guess of this psi alpha. What's another challenge of this method? The Hamiltonian itself actually is not that much of a problem. We'll see, at least for molecules, it has a very well-defined form. Yeah, keeping track of all of the degrees of freedom. For each, ignoring the nuclei, for each electron, you need to keep track of 3 position, and in principle, 3 momentum. So you have 6 degrees of freedom per electron. When you get to very large molecules, that number scales exponentially. So it would become impossible to keep track of all of that on a classical computer. So what quantum chemists do in practice is they make a series of approximations, some better than others, to reduce the scale of the problem. The most basic one and the most popular one is this Hartree-Fock method, which is kind of the most basic approximation you can make of a molecular system. It's known as a mean field approximation because what you do, in essence, is instead of keeping track of every single electron and all of its possible interactions, what you do is you look at one of the electrons in your molecule and you treat all the other electrons in the system as a cloud of charge. So you're abstracting away the position of the electrons, you're just treating them as a charge distribution so that you don't have to keep track of all the degrees of freedom of all of the electrons, and you do this sequentially for each one of them. What this approximation means is that each electron is treated independent of the others. You're no longer looking at individual electron-electron interactions, which helps you reduce the scale, but it also means that you're removing correlations between electrons. The mean field part, of course, comes from this abstraction of treating all the other electrons as a cloud of charge. And what you end up getting is a system of equations that you need to solve in what's called a self-consistent way.
The electrons are independent, but they are still quantum particles. I mean, can be in a superposition of some different states of itself.
Yeah, and that's what we'll see with the molecular orbitals that come out of the Hartree-Fock method.
Okay, good.
So if you're able to solve these equations in a self-consistent way, meaning that the solution that you get for one electron is consistent with all of the other electrons, you get an approximation to your wave function as a series of molecular orbitals that kind of describe the population of the electrons along different spin orbitals, which we'll see. So in practice, what this looks like is if you have just simple atoms, you can approximate the distribution of probabilities, or your wave function, as a superposition of some kind of basis function. In practice, to make the computation efficient, you take it as a linear combination of Gaussian wave functions. The reason you do that is because Gaussians by themselves actually aren't very good descriptions of proper wave functions, but they do make computations much easier, and if you take a series of them, or a combination of them, you can actually get pretty close to the true characteristics of your wave function. In practice, what you would do is optimize these parameters for each given atom, and then out of those optimized parameters, create your linear superposition that describes your wave function or that approximates your wave function. Once you do that for individual atoms, a molecule, of course, is a combination of different atoms. You can then superimpose a series of these atomic orbitals into molecular orbitals that are going to describe the wave function of your entire molecule. So what you're getting at here is an approximation to the wave function with less degrees of freedom than you would need if you were to treat each electron separately and considering all of the interactions with all the other electrons. All right, any questions so far? Yeah.
Is there a physical motivation to treat each stage as a Gaussian stage? Because you kind of like disturbing the ground state of the hydrogen to superactivate or anything like that, superpose?
You can think of it, so part of the motivation for the Gaussian approximation is you can think of each atom being kind of in a potential well, and if you disturb it, it can maybe behave a little bit like a harmonic oscillator. In practice, that's not really the case. The reason Gaussians are chosen is because you need to compute certain integrals that when you have a Gaussian function, those integrals simplify significantly. So that's the main reason, really, for using the Gaussians.
But the fundamental state of a single electron is a Gaussian, right? For individual atoms.
In Rydberg atoms? Yeah. For which atoms?
If you have an individual atom,
Yeah.
the fundamental state is a Gaussian, right?
Individual atom of, it is, well, it's the, like for hydrogen, it's not just the Gaussian, it's,
Not exactly Gaussian.
Yeah.
Yeah.
okay. So the Hartree-Fock method falls under a series of methods known as wave function methods. This is separately from something like density functional theory, which is a different set of approximations. As to the question earlier about the Hamiltonian of all of all molecules can be described very compactly by this equation. So you have this, by the way, we're going to be using something called atomic units throughout these. This is units that make it convenient to not have to keep track of all the constants. So you're going to see like Planck's constant missing from these. The measure or the metric for distances is the Bohr radius, things like that. So if these equations look a little bit weird to you, it's because we're using different units. This first term over here is, of course, the kinetic energy of the electrons. Here is the Coulomb interaction between electrons and nuclei. And then this other term here is interactions between different electrons. So Coulomb interactions between different electrons. Generally, these wave function methods rely on building a trial wave function with parameters that you can vary, so very much like the variational method. The idea is you construct a basis set for defining the atomic orbital. So these are the superposition of Gaussians that I talked about earlier. Using these atomic orbitals, you construct molecular orbitals as a linear combination of them. And this will approximate the wave function of your molecule in a way that you can then insert into the variational method, for example. So you can calculate the expectation value of the Hamiltonian in principle and get an estimate for something like the ground state energy. So what do you think is wrong with the Hartree-Fock method? This method, by the way, was developed almost 100 years ago. Why do you think quantum chemistry still poses a problem, even though we have this nice approximation? So think of the approximations that went into it. What did we neglect? What are we neglecting? What are we ignoring? Yeah, so one of them is electron-electron correlations. You can think of that as entanglement in the molecule. Anything else? Sorry? You are kind of taking them into account by this superposition of atomic orbitals. So the biggest issue is this ignoring of electron correlations. What that means in practice is as your molecule gets more and more complex, no matter how much more you optimize the parameters of your molecular orbitals, you're going to hit a hard limit to something like estimating the ground state energy. You're going to reach a minimum that is actually not the true minimum of the molecule. And you can see that illustrated in this graph here where the circles or the dots are experimental values of the energy, and the solid line is the Hartree-Fock approximation. And you can see that eventually you start getting a discrepancy between the exact values and the values you get from the Hartree-Fock method. That being said, this method is still, in most cases, the first step of any quantum chemistry computation, so it's still very important to know about and understand. No one really does this method from scratch anymore. There's a ton of software packages that have been developed to facilitate using this method. In particular, the Hartree-Fock method is the most useful way of constructing a good approximation to your wave function still. And we're going to see with the VQE algorithm that that's going to be our first step, is building a trial wave function that's going to be the Hartree-Fock state.
Another question. Because this is for H2, right? So small molecules.
Yeah.
So if we have a very big molecule with many, many electrons, there are some approximations, there are some papers that prove that the same classical approximation is valid. So in this case, we could ignore the quantum computer because we could use the same classical.
Yeah, so classical is still very powerful.
Or really, really big.
Yeah, for really big molecules. It ultimately depends what kind of accuracy you need for your applications. Classical computing can get you close enough for certain applications. If you're looking at different ones that you need more accuracy, then the classical methods aren't good enough for that. And that's the promise of quantum computing for this. It's to be able to get more accurate results, especially when you get very complex molecules that have a lot of correlations. As you ignore the correlations, that gap between the energy of the Hartree-Fock state and the true energy becomes bigger and bigger. So the discrepancy between your experimental values and your true values will grow with the complexity of the molecule.
Okay.
But again, it depends on how much accuracy or how much error you can get away with. For some methods, you can get away with a large error. It's good enough for the application. For other ones, you need more accuracy. So what the Hartree-Fock method does is approximates your wave function. I mentioned before that the Hamiltonian has this very nice form. If you've ever done quantum mechanics, you know that typically your Hamiltonian is expressed as a matrix in a given basis set. So what do you think happens to the Hamiltonian? Or to put it another way, do you think that describing the Hamiltonian using these Hartree-Fock states poses a problem? It depends on the problem you're looking for. We'll see tomorrow that usually you make an approximation where, because the nuclei and the electrons live in such different, or their dynamics are in such different timescales, you can often ignore what the nuclei are doing and just focus on the electrons, because anytime the nucleus moves, the electrons are so much lighter that they're going to reconfigure much, much faster. Yeah, so we'll actually see that example tomorrow where you'll have two different atoms and they'll come together and you can calculate the potential energy surface of them. In that case, we're going to look at a simple example where it's hydrogen coming together, essentially. So the position of the electrons and the nuclei are treated as the same, but you ignore the dynamics of the nuclei or the interactions of the nuclei, basically. No, not yet. So the answer to this, to put it another way, if you were given the true ground state wave function, your Hamiltonian will be diagonalized. You wouldn't have a problem. If you pick a very bad basis, then your Hamiltonian can be a very complex matrix that would be difficult to diagonalize. Happily, it turns out that in the Hartree-Fock basis, your Hamiltonian is actually very accurate for most intents and purposes. So the Hartree-Fock method is not only good for estimating your wave function, it's actually good for expressing your Hamiltonian in a given basis. So due to these limitations in the Hartree-Fock method, the quantum chemistry community has, over the past 60, 70 years, developed a range of what are known as post-Hartree-Fock methods. They increase in complexity as you account for more and more correlations that exist in your molecule. What this diagram is meant to show is the cost of having or accounting for more and more of the interactions given the size of the basis set. So you can think of this as you describe more in detail what's happening in your molecule, you're going to need more computational resources. There are typical workhorses like the coupled cluster method, the full configuration interaction method. These are techniques that were developed decades ago, but that quickly hit hard limits in terms of how far you can get using them with a classical computer. You can treat very complex molecules, so this might be, to your questions also, that you can do computations of very complex molecules very accurately. Those will likely rely on these very complicated methods, but eventually if you want to treat something like a protein or a drug molecule, it becomes really difficult to do. So this is where quantum computers are hoped to have some promise. You have all of these methods developed classically. You hit a hard limit because of efficiency of classical computations. So what we're interested in doing is using quantum computers to improve on this Hartree-Fock approximation and even improve on these post-Hartree-Fock methods that have been developed. So there has been, of course, a series of quantum post-Hartree-Fock methods developed. VQE being one of them. I would say it's questionable whether VQE will be of kind of commercial utility or not, as with all NISQ algorithms, but it's an easy enough algorithm to understand that we'll still look at it. And some people think it's still useful for preparing good states in practice. So if you're not familiar with VQE, the idea is fairly simple. We begin with a Hartree-Fock calculation. So you begin with a classical computation to approximate the state of your molecule. You can think of this as your trial wave function that you're guessing in a variational method type of workflow. Using a series of quantum gates, you're going to create an ansatz, which is you're trying to improve on the guess from the Hartree-Fock method and create a slightly more complicated wave function or a slightly better educated guess to your wave function that accounts for more interactions. Measure the expectation value of the Hamiltonian, so measure the ground state energy if you're approximating the ground state wave function. And the ansatz that is built into your quantum circuit has gates that depend on parameters that you can vary, very much like the variational method. So the idea will then be to optimize your circuit parameters or optimize your ansatz to lower that estimate of the ground state energy as much as possible. In practice, the challenge of VQE is always coming up with a good ansatz. There was a lot of work that was done in the last 5 years or so around this. We're not going to bother too much with the problem of the ansatz. Because we're only looking at small molecules, we're going to take a very simple ansatz and then just go through the workflow of the VQE algorithm. So if you're not familiar with variational algorithms and variational circuits, I'm going to give you a quick, 5-minute introduction to these. What variational circuits are quantum circuits that have gates that depend on parameters that you can vary, typically using some kind of optimization method or gradient-based method. These are, of course, the basic building blocks of variational algorithms, as well as at least early quantum machine learning that Marco will actually talk about next week. So it's very much built around the idea around machine learning or supervised machine learning, where you have a target model, you have a cost function, and you vary the parameters in a way to minimize that cost function. So the general algorithm for variational circuits looks very much like your typical workflow in machine learning. You have some kind of input. Machine learning, it would be some data. In our case, it's going to be the Hartree-Fock state, plus the additional variational gates in your circuit that are creating your ansatz. A problem-specific cost function. So the cost function is always going to vary depending on what problem you're trying to solve. You're going to have a set of parameters, typically gradients, to calculate the optimization or to vary the parameters. And you repeat this over and over again until you reach some kind of potential energy minimum. The challenge of the ansatz, of course, is whether this minimum is a local minimum or you're close to a global minimum. We're not going to spend too much time on discussing that, but it is something to watch out for. The complication of all of these methods is you never know how good your approximation is unless you can compare it to an experimental value. You only know that you can lower the energy if you improve on your guess, but you never really know how good your guess is. So the 3 main ingredients that we're going to see in variational algorithms are a circuit ansatz, which again you can think of as your guess for your wave function in this context, a cost function that you're going to minimize, and a trading procedure to minimize this cost function. These variational algorithms fall under a class of algorithms known as hybrid algorithms. The idea behind these came about 10 years ago, actually, or VQE was developed about 10 years ago, where the quantum hardware had very limited resources. So you would split the computation between something the quantum computer could do with its limited resources and something that it was good at doing. And you leave the part that the classical computer is good at, like optimization, to just a regular computer, and you interact your quantum computation with your classical computation in a way that follows the algorithm that I described in the last slide. So I mentioned before that no one really does Hartree-Fock from scratch anymore. There's software that's been developed to facilitate this. Likewise, there's a ton of software libraries developed for both simulating and running quantum computations on real hardware. So one of them is PennyLane, which is a software developed by Xanadu. So I'm going to spend a little bit of time just giving you a high-level overview of what PennyLane is. Out of curiosity, how many have heard about PennyLane before? Oh, it seems like more people have heard about PennyLane than Xanadu, curiously. Okay, so PennyLane is an open source library that focuses on differentiable programming of quantum computers. So it started off very much focused on quantum machine learning and being able to do differentiable programming, which is essentially being able to calculate gradients of just about anything. It's Python-based, so it's easy to learn, makes it easy to be open source. In particular, being open source, it's open to contributions from anyone. So if you have ideas for features that you would like to see in Penny Lane, or you find a bug or something that doesn't work right, you're welcome to contribute to the software itself. We have internal reviews of any external contributions, of course, but it is a good way of kind of getting experience with quantum software development if you're interested in that. I already mentioned that it focuses a lot on differentiability or differentiable programming. And one of the tenets of this library is we aim to make it as modular as possible. So we're only 200 people at Xanadu. There's about maybe 70 working on software. We're only going to get so many ideas. We really want to leave it to the community to create more ideas and allow them, or with Penny Lane, allow them to develop those ideas very flexibly. So we like to think of it as Penny Lane gives you building blocks that are very flexible, very amenable to things that we may not have thought of at Xanadu, but that you can still use it to build your own ideas. Penny Lane is about 6 years old now, so it's a little bit younger than Xanadu itself, and it has grown considerably since then. We've partnered with a lot of different institutions and companies to develop different features, different plugins, different applications of Penny Lane. We are at about 37 releases now. Typically every month and a half, you have a new release of Penny Lane. And it is something that we are trying to promote heavily in universities, so in training future researchers like yourself. So we've helped about 100 universities introduce Penny Lane into university curricula. So in building Penny Lane, what the software team does at Xanadu is really try to think of how can we make the use of Penny Lane as easy as possible for our users. So I already mentioned the idea of building blocks. We also provide a lot of flexibility to users. So within these building blocks, you can modify quite a bit of them. You have access to a lot of parameters that go into these. We don't really build kind of black box functions that will run algorithms for you that you're not able to modify. We have, of course, a lot of educational material and great documentation so that if you get stuck, you have resources to follow. The link is not here, but I will say we also have a discussion forum. So if any of you during the hackathon or the exercises try out Penny Lane and you have questions, we have a discussion forum that's monitored quite closely where you can ask technical questions about quantum computing or about Penny Lane. So we really try to support the community as much as possible because we depend on the community so much in building Penny Lane. So this modularity means that it's built for a lot of things. I already mentioned the other ones. The one I'll mention now is this idea of device independence. What I mean by device independence is Penny Lane is, you can, again, break it down into two utilities. One of them is a simulator. We have a range of simulators available. The one that we're going to use exclusively in this series of talks is this default.qubit, which it's a very basic simulator. It lets you get to about 18 qubits on a typical laptop. And it's really the most basic simulator that you can have. If you want to start looking into things like how noise affects your computation, then we have a device specially built for that. If you have heavier workflows, we have these lightning devices that will that essentially have, one of them has a C++ backend so that you can run your computations more efficiently, and a couple of others have GPU support. So in some cases, you can actually accommodate a larger number of qubits, something like 30 qubits, depending on the type of GPU you have available. We won't really use these lightning devices, but just so you're aware, they are available. The other side of the device independence is, I mentioned Penny Lane can be run on hardware, so it can be used to connect to hardware. We've collaborated with a range of companies over the years to build plugins that allow users to interface with, for example, IBM's hardware or Rigetti's hardware using Penny Lane directly. One thing that I want to clarify is Penny Lane doesn't give you a backdoor access to this hardware. You still need an account with each hardware provider. You're still limited by whatever access model they have, so that you might have to pay for access or you might have limited free access. But it gives you the ability to interface with all of these without having to learn a new language. So if you get stuck doing something with Qiskit and PennyLane does it better, you can use IBM's hardware with PennyLane. You can connect to a bunch of different ones using Amazon Bracket and so on. It also interfaces very well with popular machine learning libraries. So things like PyTorch and JAX interface quite well with PennyLane, which makes it very amenable for quantum machine learning applications especially. So we're getting to the point where we're going to start doing this hands-on interaction or interactive exercise. For those of you that have never used PennyLane, what you're going to see is the way that quantum circuits are represented in PennyLane are essentially as Python functions. The order in which your gates appear within this function is the order in which they operate on your qubits. And all quantum computations have to end in some kind of measurement. You need to output something back to the classical world. And this is what's going to be returned by your Python function describing your circuit. The way that this is done in PennyLane is the first step is you typically choose a device in which you want to run your quantum circuit on. So in our case, it's going to be this default.qubit simulator. You have your Python function describing your circuit, and you need something to connect the two. You need something that tells PennyLane, I want to run this circuit on this device. And the way you do that is through something called quantum nodes, or Q nodes for short. Q nodes in PennyLane are your basic unit of computation. They encompass your device and your circuit together into a single unit. It's also what you use to interface with the classical world, in quotations, because we're using a simulator. But your quantum node is what's going to take classical input data and what's going to read out your classical output from the measurement of your quantum computation. So this is what a typical program looks like. There's a very simple one, but you can see the general idea here. You create a device. You create your quantum circuit. You associate that circuit to your device through a Q node. And you can also define other functions that will run classically, for example, computing your cost function in a variational circuit, and interface between your quantum computation and your classical computation in a PennyLane program. All right, any questions about this? So just to get like a differential, how many people have never used PennyLane? Okay. So we'll go slowly through these ideas. So what does all of this have to do with quantum chemistry? In doing the VQE algorithm, you need to prepare some kind of Hartree-Fock or post-Hartree-Fock state. The way you do that, of course, is you apply a series of gates that depend on parameters. These, for us, are going to be something called Givens rotations, and that's the reason why you have these gates represented by G's that I'll talk about in a moment. And then once you prepare this post-Hartree-Fock state, you extract your ground state energy by measuring the expectation value of the Hamiltonian. The first problem we need to solve is how do you represent molecules and Hamiltonians using qubits? And this is where this idea of second quantization starts coming in. It's really the most useful way of doing this mapping between a classical description of the Hamiltonian and wave function into qubits. So the way we're going to describe qubits is as a series of spin orbitals. Each spin orbital can take at most 2 spins, and they have to be in opposing directions because they're describing electrons that are fermions and therefore can't occupy the same state. depending on the number of electrons in your molecule, you're going to populate these spin orbitals in a certain way. The state that's going to be of particular interest to us, again, is the Hartree-Fock state, which you can think of it as you organize your electrons sequentially so that you occupy the lowest spin orbitals first, and you keep going until you've filled up or you've used up all of your electrons. What we'll see is to be able to go beyond this Hartree-Fock state, you need quantum gates or quantum operations that are going to shift the organization of these electrons within your spin orbitals. These are known as excitation gates. These excitation gates are very important because when you do this kind of operation where you, for example, promote an electron from one spin orbital to another, you need to make sure that your operation is preserving the number of electrons. If you're not careful, you might make an electron disappear from your molecule and you're no longer solving the same problem that you think you're solving. We're going to use two excitation gates. One of them is this single excitation gate that will take one electron to a different spin orbital. And we also have double excitation gates that will promote two electrons to a different spin orbital. If you want a bit more information here, I put the title of a paper that really laid the foundations of this idea of excitation gates. So this is just to give you an idea. Don't worry too much about the equations, but what these given rotations do, or the single excitation gates, as I mentioned, is you can promote an electron from one spin orbital to another. You can think of this as a rotation in a subspace of your Hilbert space. So you're trying to explore a larger part of your Hilbert space through these rotations. You also have these double excitation gates where you can then promote two electrons to a different spin orbital. So what our ansatz is going to look like is a series of these single and double excitations to build a superposition of spin orbitals beyond the Hartree-Fock.
So the way I'm reading this is the first two qubits are they're the ground, right? They're in the ground state.
Mm-hmm.
There's no distinction between spin up, spin down in terms of the or in terms
Yes.
of the position.
The
Spin up is the leftmost, spin down is right.
exactly.
So in the context here, there's no such state. If you initialize that zero, there's no such, that means you don't have.
That means you don't have electrons. So if you're looking at like the hydrogen molecule, you'll have two electrons. The Hartree-Fock state will be this one.
And so it would be like if I do a circuit, I would initialize it at zero, and then I would do like flips to
Yeah.
put this spin.
Yeah, you initialize at zero, you create the Hartree-Fock state by populating the lowest spin orbitals. And then after that, your ansatz will be building other ones. Any other questions? So one important thing that I forgot to mention here is the ordering. So you'll notice in this picture, the way that you differentiate different spin orbitals, each one of them can take two spins. The left one, the leftmost one in a given spin orbital is encoding your spin up, or one of the states of your qubit. The other one is describing the spin down. In this case, we promoted the spin up to another spin orbital, and you can see that the leftmost term is now a zero, representing no spin up electron in your lower orbital, and it's been promoted to the second orbital, and now the leftmost value of your second orbital is a 1. Okay, so that's the way that you read this, and it's a similar idea here when you have double excitations. You can go from this state here to this state where now the second orbital is populated by spin up and spin down. So that's the way that you encode the state of your molecule. To represent the Hamiltonian as a qubit operator, typically the first step is to express it in a second quantization formalism, so encoding things into annihilation and creation operators, or fermionic annihilation and creation operators, as well as these coefficients that account for interactions between the electrons. In practice, what you do to find these coefficients is you have to compute these integrals. These phi's would be, for example, your Hartree-Fock state. And if you were to do this by hand, for the simplest molecule, for H2 molecule, you would need to also map your creation and annihilation operators. There's different transformations you can do. We're going to focus on the Jordan-Wigner transformation to encode or to express your creation and annihilation operators in terms of polyspin matrices. The reason you do it with polyspin matrices is because typically when you do a measurement, you do it with respect to one of these directions. Either, if you want to measure along the z-axis, you do a measurement of poly z. In the other directions, you do measurements of poly x and poly y. So, if you were to do this for H2 molecule, you will get a Hamiltonian that looks something like this. Keep in mind here that each one of these h's is integrals. So you have a series of integrals to solve. You'd have a series of mappings to transform these creation and annihilation operators into polyspin matrices. And you would end up with about 15 terms. So you can see that this gets very tedious. If you go to something like the H3 ion, you have something like 66 terms you will need to compute. So the nice thing, again, with all of these methods is there has been a range of software developed to facilitate these things, and Penny Lane is one of them, where you'll see that you can do a lot of these computations just with a single line of code. All right, so that brings us to the demo. So if you have access to the Jupyter notebook that was shared, I would invite you to open it if you want to follow along. And we'll try to do this like so. Yeah. Mm-hmm. Yeah. Yeah. So you can look at the Brevet-Kitaev one, the parity mapping. Yeah. Okay, so you should, if you open the file, you should hopefully see something that looks like this. If you've never used Google Colab, you can look for it. Well, let me. So you should get something that looks like this. If you click on that, you should get an interface that looks something like here. You can create a new notebook. You can upload the notebook that was shared with you. And you should eventually get something like this. If you open a new notebook, you will eventually get something that looks like that, okay? Oh, it's cut off. Yeah. Okay. All right. So, was everyone able to open the notebook? Good. Okay. So, the benefit of this is we're connecting to a Google server somewhere in the world. It's got a lot of packages pre-installed, so it's going to facilitate a lot of things for us. It doesn't have Penny Lane installed by default, of course. So the first step is we're going to run this first line. You're going to just say run anyway. And this is going to install penny lane on the servers that we're connecting to. It'll take a few seconds. And you should start seeing a series of lines like this. Okay. Once you've installed penny lane, you want to import penny lane. Historically, we import penny lane as QML for quantum machine learning. We're also going to import a NumPy version of penny lane. The reason for that will become clear in a little bit, but essentially, you want to have arrays that are differentiable, which native NumPy doesn't have. To differentiate between Python's regular NumPy and our penny lane's NumPy, we import it usually as PMP. So to run a given cell, by the way, you can either click the play button here. On a PC, you can do Control-Enter, and on a Mac, you can do Command-Enter. Okay, so the way that these computations usually start is you need to define the molecule that you're interested in. The way you do it is we're going to define the atoms that make up our molecule. Let me just change something here. So we're going to do this for the H2 molecule. So we're going to have 2 hydrogen atoms in our molecule. And then run this. You then need to tell the program where are these atoms located. So you need to choose a coordinate system, and you're more or less free to choose whatever you want, whatever coordinate system you want. If you're curious about the distance, the equilibrium distances between your atoms, there's a range of resources given here that tells you how to find these distances. I've already chosen a set of coordinates that I'm just going to copy here. Okay, so the coordinate system that I've chosen is I've positioned the hydrogen atoms along the z-axis, and they are both symmetrically placed along the origin. So one of them is at about 0.66 atomic units above the origin. The other one is 0.66 units below the origin. We'll see tomorrow that you can pick different distances between the atoms, and that will give you different energies, and we'll be able to construct a whole potential energy surface and actually find these coordinates back again. Yeah. Yeah, so that's what's outlined here. There's repositories, essentially, of people that have done these computations before or that have measured these experimentally, and there's databases where you can find them. So once you've defined the molecule that you're interested in, you want to build the molecular Hamiltonian in second quantized form and do the Jordan-Wigner mapping that I talked about earlier, and we're going to see that we're going to get those 15 terms that I showed you before. So to do that, we're going to build our molecule object. Penny lane has a quantum chemistry module that we're going to call. And we're going to give it as input the symbols, so the 2 hydrogen atoms, as well as the coordinates of the 2 atoms that we defined above. Once you do that, we're going to create both our Hamiltonian as well as get a value for the number of qubits that we're going to need to build this Hamiltonian. The way we do that is with this molecular Hamiltonian function that we give as input this molecule object that we created earlier. Okay, and just to speed this up and show you that we get the result that we expect, I'm just going to copy this. And whoops, I forgot to run this one. Okay, and you can see that we're going to need 4 qubits. So we're going to need 2 spin orbitals to define this Hamiltonian. And you can see a lot of the terms that I showed you before. So this is your Hamiltonian expressed in second quantized form with Jordan-Wigner mapping into Pauli matrices. Okay, and just to confirm we have the right one, you can see if we get the length of this Hamiltonian, we can confirm that we do have those 15 terms that I mentioned earlier. There's different functions that you can call. So within molecular Hamiltonian, within this function, you can add a second argument saying use Jordan-Wigner mapping, use another method. Penny Lane at the moment, I think, has 3 methods. If you have another one, then you would need to code it yourself. What do you mean by 2 to the n? The length of the Hamiltonian is how many terms you have. Yeah, each one of those terms is acting on, in some way on the 4 qubits that you have. The dimension of the Hamiltonian would be, yeah, 2 to the n. Yeah, so it's calculating the Hartree-Fock state, calculating those integrals for the coefficients, and doing the Jordan-Wigner mapping. So it's doing calculating these integrals. So you need the phi, so you also need the Hartree-Fock state, and doing this mapping. Because it knows the molecule that you have. That's why you need to give it information on the molecule and where the atoms are located. Okay. There's some additional reading here for you if you're interested in learning more about the mapping from electrons to qubits. As I mentioned, we have a lot of educational material, so here we have a demonstration of how using other mappings, if you're interested in that. So we have the Hamiltonian describing our H2 molecule. We need our initial state, which I mentioned was this Hartree-Fock state. In practice, there's a lot of, it's not trivial to program a Hartree-Fock method. There's a lot of work that needs to be done. We're going to skip over all of that and just run the Hartree-Fock method that's encoded in Penny Lane. So because we're working with an H2 molecule, we know that we have 2 electrons. The number of spin orbitals that we have is given by the number of qubits. Whoops. The number of qubits that we need to encode the Hamiltonian in. And from that, we can compute our Hartree-Fock state. By feeding the number of electrons and the orbitals into this Hartree-Fock state function. and we can get an idea of what this looks like. What do you think we're going to get as a result? What do you think is going to print out? So what would you expect? Or how would you know you have the right Hartree-Fock state? Yeah, exactly. Remember, Hartree-Fock state is you're occupying your spin orbitals progressively from the lowest one until you run out of electrons. And what you get is indeed an array describing that Hartree-Fock state mapped onto qubits. So we created the Hartree-Fock state. Now we want to create the post-Hartree-Fock state by using a range of Givens rotations or of excitation gates to improve on our estimate of the true wave function of the hydrogen molecule. So the way we'll do that. So we have our Hartree-Fock state. Our circuit doesn't know anything about that state yet, so we need to feed that into our circuit. The way we do that is using this basic state method. We give it an input array. In this case, it's going to be our Hartree-Fock state, and we tell it which qubits to use for that state. In penny lane, by the way, whenever you see wires, that's equivalent to qubits for our intents and purposes, okay? Next, we're going to build our ansatz, so try to improve on this Hartree-Fock state. Because of symmetries in the H2 molecule, we'll actually only need one excitation gate, namely one double excitation gate. This double excitation gate, remember, has to depend on some kind of parameter, which is one of the inputs to our circuit. And a double excitation gate is it operates on 4 qubits. So you need to tell it which 4 qubits it should operate on. Because of Python indexing, we start qubit number 1 will be represented by 0, and the 4th qubit will be represented by the number 3. Okay, so we've defined our quantum circuit. Now we're ready to perform the actual quantum computation. So we're going to define the device we want to run this in. So we're going to use the default .qubit simulator. For this one, you don't need to specify the number of qubits, but it's, especially if you're starting out, it's always good to specify this just so you know exactly what your circuit is doing. And you're also going to create your Q node that's going to be associated with the cost function. Within your cost function, we're going to have this circuit that we defined here. So remember, you need to have Hartree-Fock state, prepare the post-Hartree-Fock state, measure the expectation value of the Hamiltonian. What do you think our cost function is going to be in this case? What are we returning, or what are we trying to minimize? Yeah, the energy. So the expectation value of our Hamiltonian is going to be the function that we return, or the value that we return. So we first need to associate our function to the device that we defined above. We need to, as part of our cost function, we need to run this quantum circuit. So I'm just going to copy it here. The wires is going to be all of your qubits. So another way of, instead of writing out the 0, 1, 2, 3, you can just say range of qubits. Qubits here being the number 4. we're going to return the expectation value of our Hamiltonian that we associated with the variable capital H. When you have small enough circuits, it's usually a good idea to draw it out, just to make sure that what you've created is the circuit that you want. When you try to draw your circuit, you always need to feed it whatever input parameters are needed. So in this case, you need one parameter. We're just going to put any random parameter just to get a drawing of the circuit. Yeah. Mm-hmm. H is this Hamiltonian. Yeah. Okay, so what you can see here is you have a 4-qubit circuit. The first stage is mapping your Hartree-Fock state. So you start off with all the qubits in 0. You do some kind of mapping to encode the Hartree-Fock state. And then you do this double excitation gate that depends on some parameter, and you end by measuring the value of all of your qubits depending on the term in your Hamiltonian. Yeah. If you, let me see. If you go back here, we're only using a double excitation gate because we only need, going from the 1100 state, we only need the 0011 state. Because if you look at the other one, the single excitation where you exchange only one electron, you can think of it as those contributions cancel out. They represent kind of opposing terms. So that's the symmetry we're taking advantage of. Normally what you would do, a brute force way of doing it is you apply every possible excitation. You apply all possible single excitations, all possible double excitations, and you optimize the parameters that way. Here we're skipping the single excitations because we don't need them. All right, any other questions? Yeah. What do I mean by they cancel out? Their contributions in the expectation value cancel out. Yeah. Mm-hmm. There are more complicated versions that take more resources. Yeah. Okay, so we've done, or we've programmed the quantum computation part of things. If you had access to quantum hardware, this is the part that you would do on the quantum hardware. We also need to run an optimization routine to vary the parameters in a way that minimizes the energy. The way we do that is we choose the optimizer that we want. There's a whole range of optimizers. We're not going to do anything complicated. We're just going to use the simplest possible optimizer, which is a gradient descent optimizer. It has a default step size. We're going to choose a different step size for the optimization. And then whenever you do these kinds of routines, you always need to start with a guess of what your parameters should be. The guess can be more or less educated. For this type of problem, it doesn't matter too much because it's very simple. So we're just going to take any random value. We'll take 2. And this is where the difference between Penny Lane's version of NumPy and Python's version of NumPy becomes important. We're going to be differentiating this array. So we need to make it differentiable. Okay, and if you want to get an idea of where we're starting off from, you can call this cost function. Okay, and you get some value for the expectation value of your energy. Our job now is to minimize this value as much as possible. How much time do we have? We have like 10 minutes? Yeah.
10 minutes.
Okay, that should be, yeah, that should be enough time. So, if you remember the procedure to follow, this way. In our variational circuit. So what we've done so far is defined our inputs, our Hartree-Fock state, defined our cost function. We know what parameters we want. We want 1 parameter because we have 1 double excitation gate. We can calculate gradients using gradient descent, the gradient descent optimizer. And the last step that we need is repetition. We need to loop around several rounds of optimization to minimize the expectation value. So we're going to have an array that's going to store the value of our cost function as we run our repetition. We're going to store the values of the parameters as they get optimized. Whenever you run an optimization routine, you have 2 choices of how you want to decide when your optimization is good enough. You either run it for a set number of loops, or you set some kind of tolerance value. Once your optimization reaches that tolerance value, you can stop the computation. It's often good to do both as a safeguard. Your tolerance value will be determined by your application, how much error you can tolerate. However, when you have complicated problems, you often don't know how long or how reasonable your tolerance value is going to be. So it's always good to cap the number of loops so you're not running indefinitely. So we're going to do both. We're going to define a maximum number of iterations. Because I've run this problem before, I know that 40 will be more than enough. And yeah. They are the number of loops, so the number of times you're going to repeat the optimization. Yeah. It's just because I've run this before, I know 40 is enough. We're skipping a whole lot of steps where usually you want to optimize the step size, you want to choose different optimizers and so on. So there's a whole workflow that we're ignoring here. So then the last thing is you want to loop around your repetitions. So whenever you optimize, you're going to get 2 values. You're going to get an updated value for your parameter, which we're calling theta, and you want to get a value for the energy in this context. Your optimizer has a built-in function called step and cost that's going to take an optimization step, recompute the cost function, and output those 2 parameters back. You give it your cost function as well as the current set of parameters. given these new parameters, we want to save them. So we want to add them to our array or list. No, angle. Okay, this part of the reason we want to store them is it's always nice to plot how the optimization went. You should see it maybe not always decrease, but decrease in general. And it's a good diagnostic to make sure that you've done things correctly. We're going to compute the change in energy between before you did the optimization and after you did the optimization. If that change is below our tolerance value, we know that we can stop the computation. Yep. Okay. Okay, so if we've reached our tolerance, we don't need to go through the 40 iterations. We can just break out of the for loop and end our computation. I'm going to add one more thing here. It's optional, but it's a good way of diagnosing in real time the optimization routine. Okay, what this line is going to do is every second step is going to print out the new energy. And you should see that energy decrease if things are going well. Right, so let's try this. Oops. Okay, so you can see as the optimization is going, the value of the energy is indeed decreasing. So it's becoming more negative. Even though the absolute number is increasing, it's becoming more negative. After about step number 18 or 20 or 19 maybe, we've reached our tolerance value. So we stop the computation prematurely, and we can print out the final value of our energy and the optimal value of our parameter. And then the last step, I've already written it out for you, but if you follow along, you should be able to generate a graph that looks something like this. So the green dashed line is the estimate from our VQE algorithm. The red line here is the true ground state energy, considering what's known as the full configuration interaction. And you can see that we reached that full configuration interaction energy within our tolerance after about 18 steps. And then here you can also see that our initial guess was pretty bad for the parameter. We've reduced that significantly to about 0.20. All right. Yeah, so that's the VQE algorithm. Yeah. So the difference here is the amount of resources that you're using. If you're doing a computation that needs n qubits, if you're simulating that, you're actually using 2 to the n bits. Whereas if you do it on a quantum computer, you're using n qubits. So you're taking away that exponential increase in resources. That's why when you run simulators on a common laptop, you run out of memory after about 18 or 20 qubits. There's quantum computers now that exist that have more than 20 qubits, so you'll be able to do computations beyond that. Mm-hmm. It depends what you're trying to benchmark, I suppose. If you're trying to benchmark something like accuracy, you will run this computation, but the quantum circuit on quantum hardware. You can do it for a random set of parameters. There's a whole range of complications around variational algorithms that maybe Marco will talk about next week, things like barren plateaus and things like that, yeah. If you're trying to benchmark something like time that it takes, you have to account for, quantum gates are physical devices. It takes time to transform qubits. You can usually, or sometimes those specs are available, so you can see what are the native gates of the hardware, first of all. Given sortations are kind of an abstraction of several poly gates and like CNOT gates. You need to see what's available in the hardware, so it really depends what you're trying to benchmark. It's possible to be done. I would say at the moment, it's of limited utility just because of the amount of error in quantum computers at the moment. Yeah. Like physical. Yeah, so the physical interpretation of that, further down. You can see it here. So what we're doing with the double excitation gate is taking our Hartree-Fock state and building a superposition of the Hartree-Fock state plus the state that has the second orbital occupied. The angle here gives different coefficients to these two values. So it's telling you in the ground state, which state is more important, the Hartree-Fock state or the 0011 state? Exactly, yeah. Any other questions? Yeah, you can think of it as that. It's basically telling you the Hartree-Fock state isn't good enough. You need a little bit of this spin orbital as well. What do you mean by everything? To some extent, I mean, it's still running computations in the background. So. It's doing some computations. It doesn't need all the information like the radius of the nuclei and stuff. You give it the distances between the atoms. Tomorrow we'll see what happens if you vary that distance. It's recomputing like the integrals that we saw for the coefficients of the Jordan-Wigner mapping and all of that. So maybe tomorrow or Thursday, we'll talk about something called data sets, which is information like that is already pre-stored, pre-computed. You can just upload it, and you don't have to run these computations over again. The Hartree-Fock method is a way of doing it. I don't have the scaling off the top of my head, but you mean for the Hartree-Fock method or the VQE method in practice? Yeah, I don't have a good scaling off the top of my head. It is significant because you can in principle do very large computations with the Hartree-Fock method. Whether they're accurate or not is a different thing as the complexity of the molecule grows. But yeah, it's pretty significant. Yeah. Mhm. So what's going on under the hood of this double excitation gate is a series of CNOT gates that are entangling your qubits together. And that's how you're encoding more correlations between your qubits. Right.
So you're basically, so you have one cap that will never be used. So currently this base is a bit larger than what we need.
Yeah, so that's the importance of these particle conserving transformations. There's some states that you won't need. You won't need like the 1000 state. It's just not physical. Yeah. Yeah. Yeah, it's in our case, it's going to be this. You plug in the value of theta equals 0.2, and this is the final state. It's a superposition of your Hartree-Fock state and this state. Yeah, yeah, you can do that. Well, I'll clarify. You can do that in a simulator. In real hardware, it's a lot more expensive to do. In the simulators, because it's just doing linear algebra in the background. In hardware, you would have to do a whole state tomography to evaluate like the coefficients and the states and all that. The way you can do that, instead of in your circuit, instead of returning the expectation value of the Hamiltonian, you can just return the state. So it's literally changing this to that, and you can see the state. I won't do it now because it takes a little bit of time to like translate, but in principle, you can do that. Thanks. All right.
Okay, I guess, thank you.